We're going to talk about constraint propagation or constraint satisfaction problems, which we saw in lecture sometime last week, I believe. So we're going to start with an example and then go into these different strategies for solving constraint propagation problems, some of which will have a bigger tree and result in more backtracking, and others will be more efficient and allow you to eliminate more options early on. So we're going to start with a problem from 2009 Quiz 2, where MIT is having a time travelers convention. So they've invited a bunch of famous scientists from the past to come and speak in the present day. So they've invited Newton, Bohr, Curie, Turing, Lovelace, Pythagoras, and Socrates. And there are 4 time slots at which these people can speak. So they can talk at 1 p.m., 2 p.m., 3 p.m., or 4 p.m. But the thing is, there are constraints on some of these because certain groups of students want to see multiple of these people, so they don't want them talking simultaneously. So we're told the course 8 students want to see the physicists, Bohr, Curie, and Newton. So we're going to draw lines between Bohr and Curie, Newton and Curie, and Bohr and Newton, indicating that none of them can talk at the same time. So these lines are called constraints. And in this case, they're just not equal constraints. These people can't be at the same time. Then the course 18 students want to see the mathematicians, Lovelace, Pythagoras, and Newton. So we'll draw lines between them also. Also, if you don't want to copy all of this down, one of the handouts has copies of this graph. The members of the Ancient Greece Club want to see the ancient Greeks, Socrates and Pythagoras. So we'll draw a line there. The visiting Wellesley students want to see the female speakers, Lovelace and Curie. The CME students want to see the British speakers, Turing, Lovelace, and Newton. We already have a line between Lovelace and Newton, so we'll just get the other 2. And then finally, you decide that you will only be happy if you get to see both Curie and Pythagoras. And then the last piece of information we're given is most of these people are free at any of the 4 hours, except Turing has to get home early to win World War II. So he can only speak at 1 p.m. So we'll put a 1 there. So everyone else can speak at any time, so we'll give them all the numbers. And this set of numbers is called a domain, which is the set of possible values that the variable can take. So some terms that we just got are, this thing is a domain. Each of these numbers is a value. And these letters are variables. So now we're going to try to assign each of these people to a time slot. And we're going to first do a simple method, just plain depth first search. So in depth first search, we're going to make assignments, and after we make each assignment, we'll make sure that it doesn't conflict with the previous assignments. So depth first search makes assignments. And checks for contradictions with past assignments. So let's do this over here. So we're going to start by assigning Turing. One reason is because that's what this particular quiz problem says to do, but we might also say it's because he has the smallest domain, so he's clearly fairly constrained. One note there, you could also argue that Newton is the most constrained because Newton can't be at the same time as any of 5 other people. but you could call either of these most constrained. And so on a quiz, it would tell you exactly how to decide. In this case, we're going to assign them in the order Turing, then Lovelace, then Bohr, Curry, Socrates, Pythagoras, and Newton. So we're going to start making a tree, and we're going to start with Turing at the top, and we'll say Turing can only be at 1, so we'll just assign Turing to 1 p.m. And according to this, we have to check for contradictions with past assignments, but there are no past assignments, so we're all good. So next we'll move on to Lovelace, who has 4 options, 1, 2, 3, and 4. So we'll build a tree from Turing's option. And we'll try assigning Lovelace to 1. Does that work? Why not? Yeah, because this line means that Turing and Lovelace can't be at the same time, so Lovelace at 1 doesn't work. So we're going to backtrack there. And we'll try assigning Lovelace to 2 instead. So backtracking is basically when you get to a dead end in the tree and have to go back up and try another branch. So we backtrack and assign Lovelace to 2, and it looks like that works. So then we can move on to Bohr. And we'll try Bohr at 1 p.m. first. Does that work? Yeah, Bohr doesn't have any constraints with anyone who's assigned already, so we're good. And then Curry, how about Curry at 1? Can Curry be at 1? No, Bohr. So we'll backtrack and assign Curry to 2 instead. So we tried 1, it didn't work. Tried 2, does 2 work? No, because Lovelace is at 2. But 3 works because no one else is at 3 yet. So then we get to Socrates. And we'll try Socrates at 1. Does that work? Yeah. OK, and then how about Pythagoras at 1? No, because Socrates. Pythagoras at 2? No, because Lovelace. Those don't work. How about 3? No, because Curry. Does 4 work? OK, so we tried a bunch of things. So we're having to backtrack a lot here. And then finally, we'll assign Newton. So it looks like we're almost done. Can Newton be at 1? No, how about 2?
No.
3?
No.
4? Uh-oh, so now what? So we've tried all of these and none of them work. Where do we backtrack to? Yeah, so we would have to backtrack back up to there and continue building the tree from there. But this might go on for a while, so instead we're going to try a more intelligent method. So we're going to add on something called forward-checking. Basic idea of forward-checking is every time after we make an assignment, in addition to checking for contradictions, which is the depth-first search step, we're going to cross off values from the neighbors' domains if they conflict with the assignment we just made. So after each assignment, we'll eliminate incompatible values from the neighbors' domains. So if we eliminate values by crossing them off, what would happen when we backtrack? We can just get there and find out. OK, so I'm going to reset the domains on this graph. We'll see if we can solve this problem faster with forward checking in addition to depth first search. So we'll do them in the same order. We'll start with Turing again. So this was our first method, just plain depth first search. Now over here we'll try our second method, depth first search with forward checking. So first we'll assign Turing to 1. And we check for contradictions. There are no past assignments, so it doesn't apply. Then we do forward checking. So we're going to look at all of Turing's neighbors, and we're going to see if they have any values that are incompatible with Turing being at 1. So do they?
Yes, so n and l both can't be 1.
Yeah, so n and l can't be 1. So we'll cross off n can't be at 1, and l can't be at 1. OK, and those are all of Turing's neighbors, so we're done with forward checking. So now we get to Lovelace. What values are still in Lovelace's domain? 2, 3, 4. So already our tree is smaller. So now we've saved the trouble of attempting to assign Lovelace to 1. And we try assigning Lovelace to 2. It turns out if you're doing forward checking, you no longer need to check for contradictions with past assignments because forward checking ensures that there won't be any contradictions. So we'll skip over that and we'll get to the forward checking step. So now that Lovelace is at 2, are there any values in Lovelace's neighbors that are incompatible?
Yes.
Which ones?
For n, c, and p.
Yeah, so Lovelace's neighbors can't be at 2, so we'll cross off 2 from n, c, and p. OK, then we get down to Bohr. It looks like Bohr still has all 4 options. So we'll assign Bohr to 1. And we already know that will work with past assignments. Can we cross off anything from Bohr's neighbors? One from C, yeah. And it looks like Newton already has 1 crossed off, so nothing happens there. OK, then we get down to Curry. What values does Curry still have?
3 and 4.
3 and 4. So our tree is smaller here too, which is nice. So we'll assign Curry to 3. Can we cross off anything?
L.
So L has 3 still, but L is assigned, so we're going to talk about that in a sec. It looks like also Newton can't be at 3 now, and Pythagoras can't be at 3. So Bohr and Lovelace appear to still have 3 in their domains, but the thing is, they've already been assigned. So what's going to happen if we have to backtrack is it's like pushing an undo button. Basically, you would uncross off a bunch of things and undo an assignment and then redo someone's assignment. So like if we had to backtrack at this point, then we would undo the things we had just crossed off and reassign Curry to 4. So it turns out it's not going to make any sense to cross off values from the domain if the variable is already assigned, because you would just have to undo that before reassigning them. So it won't actually save you any trouble. But we can add how backtracking works here. So when backtracking, we'll uncross out values. And here, eliminating is the same thing as crossing out. And actually, in Lab 4, in which you'll be coding these algorithms, I think the convention is when a variable is assigned, it's as if all of the other values in its domain get eliminated because it's already been assigned. So in that case, the value 3 just wouldn't exist, but that's just an implementation detail. Okay, so we're done with Curry, and now we get on to assigning Socrates. So Socrates still has all 4 values. So we'll assign Socrates to 1. Can we cross off anything from assigning Socrates to 1?
P.
P. Pythagoras can't be at 1 now. Okay, and then we assign Pythagoras. What values does Pythagoras have left?
4.
Only 4. So we'll assign Pythagoras to 4. And now what can we cross out? Newton can't be at 1, and everyone else is already assigned. I mean, Newton can't be at 4. Uh-oh, so now Newton has no values left. So there's an implicit escape clause that's written as note 2 on, there's a handout that has a whole bunch of words on it. There's a thing that says note 2. If any variable ever has no values left, then we'll backtrack immediately, because even if we're not planning to assign them for a while, the problem is already unsolvable, so we might as well backtrack. So in this case, we would backtrack, and where would we go to? Yeah, Socrates at 2. So we backtrack to the same place that we did the first time around, but we have a much smaller tree and we didn't have to do as much work to get there. So that's good. This saved us some work and less things in our tree. But we still have to backtrack a bit. So let's try another method and see if it's even better. So we're going to add on to here propagation through Singleton domains, which I'm abbreviating as prop1. So we're still going to do the depth first search and forward checking steps. But now what's going to happen is after we do those, we're going to check and see if we've reduced any domains to a size of 1. So after depth first search and forward checking, check for newly created Singleton domains. And if we find one, then we're not going to actually assign the variable yet, but we'll hypothetically think about, given that this variable can only have this one value, what does that mean that other variables can't have? So we'll use that to cross off values from that variable's neighbors. So if we find a singleton, we won't assign it yet. But we'll use it to eliminate values from its neighbors' domains. And then if that creates a new singleton, then we'll propagate through it, and we'll continue this until we stop creating new singletons. So if this creates a new singleton, we'll propagate. So let's try that with this problem and see how it changes. So we'll make a third tree here, where we do depth first search with forward checking and propagation through singleton domains. I'll reset these domains again. So one question you might ask is, what about Turing? Turing is already a singleton domain, because a singleton domain is a domain that has only one value. And so you might ask, why don't we propagate through Turing? Why does it say only newly created singleton domains? So one answer is that this is a bit of an implementation detail. You could have an algorithm that propagates through every singleton domain. Another good answer is it's more efficient to only propagate through new ones, because otherwise, if, say, you reduce Lovelace to have a singleton domain, then every time you do anything else, you'll have to continue repropagating through Lovelace, and that won't actually do anything new because you've already crossed out the value from Lovelace's neighbors. So we'll start with depth first search again. So we assign Turing to 1. And then we have forward checking. So what do we cross out? Newton and Lovelace 1. So this is the same as the previous method so far. And now we ask, have we created any singleton domains? Have any domains been reduced to one value? Not yet. So we'll keep going. And now we have Lovelace has 2, 3, and 4. So we'll try assigning Lovelace to 2. What do we cross out? C, P, and N. OK, now do we have any singleton domains? No, so we've reduced some domains, but they still have at least 2 values in them. So we'll keep going, and now we'll try Bohr. Bohr has 1, 2, 3, and 4. We'll assign Bohr to 1. Can we cross out anything? Curry can't be at 1 now. Now, do we have singleton domains? No, so far this isn't doing much. And you might ask, well, why don't we just propagate through the domains anyway? And it turns out if you only have not equal constraints, it's not going to do anything, because propagating through, for example, Curry's domain would mean saying, given that Curry is going to be either 3 or 4, what can we cross out from Curry's neighbors? And the answer is nothing, because we don't know whether Curry will be in 3 or 4. So we have to keep waiting until we get a singleton domain. So we'll try Curry now. We assign Curry to 3. What can we cross out?
N and P.
N and P can't be at 3. Now, do we have any singleton domains?
Yes.
Yeah, so now we have Newton is a singleton domain. So now we're going to propagate through Newton. So we're not going to assign Newton, but we're going to say, given that Newton can only be at 4, what values can we cross out from Newton's neighbors?
P is 4.
Yeah, so now that means that Pythagoras won't be able to be at 4. OK, so now have we created any new singleton domains? Yeah, so now we have Pythagoras. So now we'll say, given that Pythagoras can only be at 1, can we cross out any values from Pythagoras' neighbors? Yeah, so now Socrates can't be at 1. OK, have we created any new singleton domains? No, so now we're done. OK, so now we can continue building our tree, and we get to Socrates. And now Socrates only has 2, 3, and 4. So this is looking promising, because before we kept having to backtrack to put Socrates at 2, and now we're there right away. So we assigned Socrates to 2. Can we cross out anything from Socrates' neighbors? No, 2 is already crossed off. So then we get to Pythagoras. What values does Pythagoras have? 1. So we'll assign Pythagoras to 1. Can we cross anything out? No. And if we can't cross anything out, then there won't be any newly created singletons, which is why I was skipping that step. So then we assign Newton to 4. And it looks like we're done. So now we've found times that everyone can speak at this conference. So now if you were asked who will be speaking at 1 p.m., we could just read it off of this tree and see that Turing is at 1, and Bohr is at 1, and Pythagoras is at 1. And you could also figure out who is at the other times by seeing where we assign them to. So are there any questions on this so far? Yeah?
What was the reason why we went in the order TLPC?
Just because the problem said to. Yeah, and it's actually not a very intelligent order because Newton has these 5 constraints with other people and we did him last. That's sort of like doing Texas last. So that wasn't actually a great idea, but it illustrates something, so yeah. Any other questions? Okay, so now we're going to talk about this 4th method. But it's actually not going to be very interesting with this problem because we only have the not equal constraints. Yeah?
When we're implementing the lab, do we have to backtrack?
I believe you do have to backtrack in the lab, yeah. So actually we did, a good question is how does backtracking work? So we actually did backtrack a couple times in here. So each time we crossed off something and built the tree from somewhere else, that was backtracking. And so you would do the same thing if you had to backtrack here where you would continue the tree from 2 and it would actually look like this part of the tree. So it actually wouldn't go on that long in this case. Other questions? Okay. Is it okay if I erase this? So for this next part, we're going to look at a problem from 2011 quiz 2. And in 2011, MIT was celebrating its 150th anniversary. So in this quiz problem, MIT has acquired a bunch of animals and decided to open a zoo in Killian Court. And they have 4 pens in the zoo. And the question is, how do they assign the animals to different pens so that the animals don't fight and eat each other? So we're actually just going to look at a segment of this problem because the entire problem takes a while to do. So in this part of the problem, there are 3 pens in the zoo, labeled 2, 3, and 4. So 2 and 3 are adjacent, and 3 and 4 are adjacent. And we have 3 animals. So there are actually a whole bunch of animals in the original zoo problem. There's a meerkat, and a boar, and a hornbill, a lion who wants to be king, some other animals. But we're going to just look at the hornbill, an antelope, and an evil lion. So we have these 3 animals, and we're told that the evil lion hates everyone and doesn't want to be with any of them. So we'll draw lines between the evil lion and each of the other animals. And we're also told that the evil lion really wants to eat the antelope, and he wants to eat the antelope so badly that even if they're in adjacent enclosures, he's going to find a way to eat that antelope. So now we have this additional constraint. We'll put a mark on there saying that they can't be adjacent. We can also write this means not same or adjacent. And then we're told that the hornbill and the evil lion can be in any of the 3 pens. But because of the different habitats in the pens, the antelope can only be in 3 or 4. And so now the question is, what pen does each animal end up in? So we're going to add to this list propagation through any reduced domains. And then we'll try this 4th method. So this will be the same idea as propagation through singleton domains, except that we don't care whether they're singletons. So we can say this is same as propagation through singletons, but we'll propagate any domain that has been reduced. And then we'll have to figure out how that actually works. So let's start doing this problem, and then we'll come back to the question of how to propagate a variable in general. So we're going to assign these guys in the order. We'll try the hornbill first, and then the antelope, and then the evil lion. So what options does the hornbill have? 2, 3, and 4, because we haven't eliminated anything yet. So we'll build a tree with those. And let's try assigning the hornbill to 2. So then we're going to do our forward checking step. So what do we cross out if the hornbill is assigned to 2?
Evil lion.
The evil lion can't be in 2. And then we have this domain reduction step, because we're doing this fourth method. So which variables' domains have been reduced? The evil lion. So we're going to establish a propagation queue. We'll put that over here. And we're going to put on anyone whose domain has been reduced. In this case, it's just the evil lion. But if we had reduced multiple variables, then we would just put them all on here and probably put them in alphabetical order, just so that it's not arbitrary. So now the way that we're going to propagate through the evil lion is we're going to say, given that the evil lion can only be in 3 or 4, what values in its neighbors are incompatible with all of the evil lion's options? So I'll write that over here. How to propagate a variable. And this is the same procedure we followed for propagation through singletons, except that it was simpler there. So we'll consider all of the variables' options. And then for each neighbor of the variable, if that neighbor has a value that is incompatible with all of these options, we'll cross off that neighbor's value. So for each neighbor, if the neighbor has a value that is incompatible with all of the original variables' options, cross off the neighbor's value. And then finally, the propagation part means that we're going to continue doing this through different variables. So if a neighbor is reduced, we'll add it to the propagation queue. And we could put an asterisk here saying if we're doing only propagation through singletons, then it's only if it's reduced to size 1. So for propagation through singletons, reduced to size 1. So now let's try doing this with our evil lion. So we're told that the evil lion can only be in 3 or 4. So we'll look at each of its neighbors, the hornbill and the antelope. The hornbill we're not going to cross out anything from because he's already assigned. So then we look at the antelope. And now the question is, given that the evil lion will be in either 3 or 4, is it possible for the antelope to be in 3?
No.
No, because they can't be in the same cage or be adjacent. Is it possible for the antelope to be in 4? No, that doesn't work either. So if the antelope still had values left, we would add it to the propagation queue. But in this case, there's this escape clause where the antelope has no values, so we're just going to have to backtrack. So this can get pretty confusing if you're crossing off values and uncrossing off values. So we're going to add in a table to keep track of what's going on. This is a table that you'll also see on recent year's quizzes. So we can we'll have 3 columns. We'll have the variable that was assigned or propagated. And then we'll have values eliminated from neighbors. So note that we never actually eliminate values from the variable that we're propagating. So if we're propagating the evil lion, we'll never cross off something from the evil lion. You only cross out from neighbors. And then we'll have a column, we can put a check mark if we backtracked. So if we rewind to the beginning of this problem and fill in this table, we start it with assigning the hornbill. So we would write the hornbill was assigned to 2, and that caused us to eliminate 2 from the evil lion. So that gave us the evil lion can't be 2. And at that point we didn't have to backtrack yet, but then we propagate it through the evil lion. So the evil lion wasn't actually being assigned, so I'm just writing the variable there. And that caused us to eliminate 3 and 4 from the antelope. And then we had to backtrack. So this way we can sort of keep track of what we're doing as we go along so it doesn't get too confusing with the crossing things out and uncrossing things out. So now when we backtrack, we'll reset the antelope's domain to be 3 and 4. And we'll reset the evil lion's domain to be 2, 3, 4. 2 didn't work for the hornbill, so we'll assign the hornbill to 3. Now we're done backtracking because we've gone to the next thing in our tree. Now we have the hornbill is 3. So what happens next?
So evil lion can't be 3.
Yeah, so now we're doing forward checking, and we see that because the hornbill is assigned to 3, the evil lion can't be 3. So here we put evil lion can't be 3. And so we should have reset our propagation queue, and then we add the evil lion back in. So now we have to propagate through the evil lion. So the evil lion gets dequeued. So now we're asking, given that the evil lion can only be in 2 or 4, what values in its neighbors are incompatible? So this tells us that the antelope cannot be 3 because otherwise the evil lion would necessarily be adjacent to the antelope. Can the antelope still be 4?
Yes.
Yes and no. Why or why not?
Unless the evil lion is 2.
Yeah, so the thing is, if the evil lion is 2, then the antelope can be in 4, but if the evil lion is in 4, the antelope can't be in 4. So right now what we're trying to do is we want to see if there's a value that's incompatible with all of the evil lion's options. So in this case, the antelope being in 4 is compatible at least with the evil lion being in 2, so it's still possible that the antelope will be in 4, so we won't cross that out. So here we just have the antelope can't be in 3. So now we ask, have we reduced any variables' domains?
Yes.
Yeah, we reduced the antelope's domain. So we're done with the evil lion, but now we're going to add the antelope onto our propagation queue. So now we have to propagate through the antelope. So now we're going to ask, given that the antelope can only be in 4, are there values in the antelope's neighbors that are incompatible? Yeah, so now we can say that the evil lion can't be in 4. Because given that the antelope can only be in 4, that doesn't work for the evil lion. Does the evil lion being in 2 work? Yeah, it still works. Okay, so we're done with the antelope. Have we reduced any variables? Yeah, so now the evil lion goes back on our propagation queue. So this can go on for a while, but it'll make our tree a lot smaller. So we propagate through the evil lion, and now we're asking, given that he can only be in 2, can we cross off any values from his neighbors? No, not anymore, because the antelope being in 4 works with that. So we'll still put a row for the evil lion, but we'll say nothing happens here. We'll put none. Okay, so we finally finished that step. So now we can go on to our next assignment. So now the antelope only has 4, so we'll assign the antelope to 4. Can we cross out anything from that? Can we cross out anything from assigning the antelope to 4? No. So nothing there, and then we just assign the evil lion to 2, and it looks like we're done. Okay, so one more thing we're going to go over is the idea of reducing the domains before search. Yeah?
From 3?
Shouldn't which be? Yes, you're right. Good call. Yes, that tree should come from 3. Yeah, because 2 backtracked. So the last thing we're going to look at is domain reduction before search. So far we just dove straight into all of these searches and started making assignments before trying to eliminate any incompatible values. But there's another procedure called domain reduction before search, which is basically this, except that we're going to put all of the variables into the propagation queue. So let's try doing that with the same problem. So I'll reset our domains. And so this time we're not going to make any assignments at all. We're just going to try to eliminate values from their domains. So we had 2, 3, 4, 2, 3, 4, and 3, 4. Is it okay if I erase the table? Okay. So we're going to put all the variables into the propagation queue in alphabetical order, just to break ties. So we get the antelope, the evil lion, and the hornbill. And so we'll start by propagating through the antelope. So now we're going to ask, given that the antelope can only be in 3 and 4, can we cross out anything from its neighbors? Yeah, so that means that the evil lion can't be in 4 because regardless of whether the antelope is in 3 or 4, the evil lion in 4 doesn't work. Is there anything else? Yeah, the evil lion can't be in 3 either because the evil lion would either end up in the same pen or an adjacent pen. So we can eliminate the evil lion can't be in 3 or 4. So now we're done with the antelope, but we've now reduced the evil lion's domain. So should we add the evil lion onto the propagation queue? So this is actually an implementation detail, and we're going to say because the evil lion is already on here, we're not going to bother adding it again because it's already coming up anyway. So in this case, we don't need to. So now we get to the evil lion. And we say, given that he can only be in 2, what can we cross out from his neighbors? So antelope can't be in 3 because they would be adjacent. And how about the hornbill? The hornbill can't be in 2 because they can't be the same. So now we're done with the evil lion, but we've reduced the domains of the antelope and the hornbill. The hornbill is already in our queue, but we need to add the antelope back on. So then we get to the hornbill. We see the hornbill can only be in 3 or 4. Can we cross out anything from the hornbill's neighbors? Looks like the hornbill only has 1 neighbor, and the evil lion being in 2 still works. So nothing to do there, and we're done with the hornbill. And then we have the antelope, can now only be in 4. Can we cross out anything from the antelope only being in 4? No, so we're done. So now we haven't actually, this procedure hasn't actually built a tree or made any assignments, but it's reduced the domain so that when we do begin the search, there'll be a lot less work to do in the tree. So this is another implementation choice. When you're doing a problem, it'll tell you either reduce domains before search or don't reduce domains before search, and then you know whether to do this thing where you add everyone to the queue. So to summarize what we looked at today, we talked about depth-first search, which makes assignments and adds things to the tree. And then all of these other things, forward-checking and different types of propagation, which don't actually add anything to the tree, but they cross out values from the domains and result in the tree being smaller later on. So that is constraint propagation.